Greetings, Algebra 2 students. Today we're going to begin a brand new unit that's going to have a completely different feel than pretty much everything that we've been doing for about the past 5 months, and that should be a refreshing change to you guys. But we're getting into a topic in mathematics that is referred to the conic sections. So please copy down the title, Introduction to Conic Sections, as well as the objective for today. And our objective is to acquire a basic knowledge of and understanding of the nature of conic sections. As I said, this is going to have a completely different feel to it. It's a lot different than continuing to talk about the parent functions over and over and over again. Okay, so maybe this will get a little bit of a refreshing change going on with our material. Okay, let's take a look. Now, in mathematics, there is a topic of study that is referred to as analytic geometry. And analytic geometry is kind of a precursor to getting into the topics of calculus. Now, believe it or not, we have been actually dabbling a little bit in the topics of calculus because whether you understand it yet or not, pretty much everything in mathematics is related to everything else. So a lot of the curves and skills and things like that that we've been looking at with our graphs and equations do have direct applications into pre-cal and into calculus. So for those of you that end up heading that direction, you will recognize a lot of the stuff that we have been doing as you continue to move forward. But the topic of analytic geometry is based upon cross sections of a simple structure, and that structure is the cone. Now, if your geometry teacher did what they should have done, you would know what a cross section is, and this is the idea that a plane passes through a solid object, and then we become interested in the shape of the surface that is created when the plane passes through and cuts our solid open. Okay. Now, as I said, we're looking at the cone, but it's actually a little bit more complicated structure than that. It's what we call a double napped cone. And that is what happens when you take two cones and place them vertex to vertex. Okay, so that their main axis, their heights, so that those are perfectly aligned as if they were a single line. It's called a double napped cone. And when drawn or graphed, it looks like this. Okay. Now the idea of cross sections, as we said, is based upon cross sections. And as I hopefully reminded you a moment ago, cross sections are the result of passing a plane through a solid at various positions and angles and things like that. And as you can imagine, when the plane passes through at different angles and positions, different types of shapes are what am I trying to say? Different types of shapes are generated by the cut of this double napped cone, and these surfaces are called conic sections. Okay, so if a plane is passed through this double napped cone at various positions, many of the curves we study in algebra and geometry as well are generated, and they are referred to as the conic sections. Okay, so let's take a look at the four basic conic sections that are of interest in Algebra 2. Okay, so our first one, its main property is going to be that a plane is passed through our double napped cone perpendicular to the main axis. Okay, so a visual graphic of what was just said would be that. Okay, plane passing through. And it can pass through anywhere in the double napped cone as long as it possesses the property that the main axis that runs through the double napped cone and this plane are going to form a right angle with each other at that intersection. Okay, so that's the graphic that would show what this definition says. I know we're not all artists out there, so just do the best that you can to get yourself a diagram going so later on you can actually hopefully recognize what it is that you drew. Okay. And the idea of a conic section is we're going to take that blue object out of the double napped cone, or essentially we're going to open the cone up and look right at this new surface that is created by the fact that that plane cut the cone open. And if you pull that cone apart and look directly at the object and look at that shape, what we see is this guy. And to nobody's surprise, we have the circle. Okay, circle is the result of the cross section of the cone where the plane is perpendicular to the main axis. This is one of the main conic sections that we are going to be studying in this unit, the circle. Okay, now let's say that the plane this time is passed through the double napped cone such that it is not perpendicular to the main axis. Okay, so if that happens, we might be looking at something like this. Okay. Now, once again, obviously we have a main axis running down through our cone, and quite clearly the intersection there at the plane and the main axis is not 90 degrees. Okay, so if we extract that surface from the double napped cone, kind of open the cone up at that cut and take a look at the shape that is generated. The shape that's generated, a lot of times people want to call it a circle, okay, but if you actually get to measuring it, you're going to find a circle that is longer on one axis than it is on the other axis. Okay, and that would, in plain English, we would want to probably call that an oval, but the actual term for this in math is an ellipse. The ellipses are going to be another of the conic sections that we are going to be interested in looking at in Algebra 2. Okay, a third one would be what happens if you pass the plane through the conic section or through the double napped cone such that your plane is actually parallel to an external edge of the cone. Okay, so if you do that, we might be looking at something like this. Okay, and of course the property that the definition establishes is that we have to be parallel. Hopefully you remember back from your geometry days, put the little triangles on the line that designates parallelism. Okay, so if our plane passes through our double napped cone, okay, parallel to one of the external edges of the cone. Now obviously it's only going to hit one end of the double napped cone, and if we extract that cross section from the figure, then what we have is this guy. And hopefully you recognize him. We spent about 2 months working on the quadratic formula, the quadratic equations, and the parabola. Okay, so this is the nature of the parabola as far as cross sections are concerned, and this will also be one of the cross sections that we will be working on in Algebra 2. Okay, there is one more cross section that is going to be a topic of interest for us on the conic sections, and this one would deal with the possibility that a plane might pass through our double napped cone such that it is parallel to the main axis of the cone. Okay, well now this one becomes increasingly difficult to draw. Okay, sometimes it's hard to get three-dimensional representations to look right on a two-dimensional surface, such as a screen or a piece of paper. Okay, but hopefully I'll get the idea here through to you. We have a plane that's passing through, and it's going to be parallel to the main axis. Well, there's the main axis inside of our double napped cone, and there's our parallel markers so that we can see that yes, it is parallel. Okay. Now, when this happens, if you take the cross sections and extract them from the cone, of course, this is the first time we've actually hit both of the cones at the same time. And the result of that is what you're looking at now. Now, this is a new shape to us, a new graph. We're not familiar with this one yet. It looks like two sides of the same parabola. And the term that we have for that is hyperbola. So hyperbola is going to be kind of the last new graph or new item that we're really going to come across in Algebra 2 this year. Hopefully the idea of circle and ellipse and parabola were already familiar to us, even if we don't fully understand everything that's going on with them. Hopefully we will by the end of the unit, but we have a new topic here, and that is hyperbola. Okay, just a couple other tidbits of information that we're going to need in order to get us started this unit. Okay. Now, the general quadratic equation, as I already said, we spent a couple of months working on quadratics and quadratic equations and parabolas and stuff like that, but we did not reveal the entire quadratic equation to you. And don't freak out, but here it is. Okay. The equation says ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Now, don't shut down and think, oh my gosh, I'm never going to understand this unit at all. I might as well just quit now. Don't panic. Okay, it's very rare that any of the equations that we're going to be looking at are actually going to use all of these terms. And how they are not going to use all of these terms is that these guys A, B, C, D, E, and F, they are constants. And the good thing about constants is that sometimes constants equal 0. Okay, so if you really get to thinking about it, the quadratics that we did, okay, back in December and January, we had an A term, we had a D term, and we had an F term. And that was all. There was no XY term. There was no CY squared term. There was no EY term. And the reason that those terms did not exist was because B and C and E happened to be 0. They were not needed in order to graph our parabola. Okay, so graphing all of our other stuff, the ellipses and the circles and the hyperbolas, we won't need all of those terms for all of those guys either. It'll just depend on what kind of a graph we're working with. So it's not actually as hard as it appears. Okay, little side note on this. There are, of course, many combinations of constants and variables there. Okay, so there are going to be many graphs possible. All right, so as you kind of already saw in that little demonstration I gave you, depending on which terms from this general quadratic equation are actually participating, we get different styles of graphs. And as we activate or shut down different terms, we change the nature of those graphs. So all four of these conic sections that we looked at a few moments ago, they are all going to come from this equation depending upon which terms have non-zero coefficients and which terms are zeroed out. Okay, there's only one restriction that we have to think about as far as the quadratic. Okay, and that would be that A and B and C, those three first terms, may not all equal 0. And if you think about that, that makes perfect sense, because what happens if you take away the A term and the B term and the C term? All you are left with is x in the first dimension, y in the first dimension, and a constant. That's not a quadratic equation. That would be a linear equation. Okay. All right, one little math fact that we need to take a peek at, and then I'll leave you alone, and that would be this. Okay. We've got something that hopefully you've been introduced to in the past, but we need to make sure that we've got a firm grip on it now. Let's say hypothetically we take a number like -5 and square it. Okay, obviously -5 squared Okay, the result of that would be positive 25. You have negative 5 times negative 5. That is positive 25. Now, for those of you that are calculator people, be very, very careful. The calculator thinks negative 5 squared is negative 25, so please be smarter than the calculator. Okay. But we know for every operation in mathematics, there should be an equal opposite operation that can undo something and bring back what you had to start with. So if we took negative 5 and squared it and got 25, there ought to be some operation that we can do to 25 that will get our negative 5 back. So let's take a look. If we do the opposite of squaring, okay, which is a square root, we should get our negative 5 back. Okay, so let's take the square root of 25. Okay, now I think everybody would tell me that the square root of 25 is precisely 5. Okay, so the question is, all right, well, what the heck happened to our equal sign, or our negative sign? We started off with a negative 5. We did two operations that were opposite of each other, and we did not get our problem back. Something must be wrong. Okay, well, there is something wrong. Okay, mathematics is not a perfect science. Okay, there are some things that happen in mathematics that we cannot describe. We cannot get a firm grasp on. And as a result, what we have to do is just kind of accommodate these little failures that we don't know how to deal with yet. Okay, so to be technically correct, we are going to need to acknowledge that when a number has been squared, it's possible that that was a positive number that got squared. It's also possible that a negative number got squared. And in either case, we ended up with a positive value. So if we take the square root of a number, we have no way of knowing, was it a positive number that got squared or was it a negative number that got squared? We just don't know. Okay, so when we take the square root of a value, and this means when you cause a radical to happen in a problem, okay, you have to acknowledge that that could be a positive 5 that ended up in that 25, and it could have been a negative 25 that ended up in that value. And that's actually going to be an important math fact for the way that we go about graphing our conic sections when it comes time to start graphing them. Without this little fact, you're probably going to drive yourself crazy with plugging numbers into equations. Okay, but anyway, that is pretty much it. I appreciate you taking time to get your notes taken care of, and I will see you in class.